saw in the lab was that as you increase the temperature of a chemical reaction, the rate also increases. What we didn't see was that this isn't a linear relationship. So if you actually take a look at the rate of a chemical reaction as a function of temperature, what we see is the temperature goes up, the rate has a tendency to increase quite rapidly. So it's not quite a linear relationship. We can understand this, or we can rationalize this from just what we know about things like gases, even though some of it also applies to solutions. You know, I mean, reactions are molecules smacking into molecules. And these molecules are undergoing collisions to produce products, new products that come out. And what we see is that the more collisions we have, the more kinetic energy that we have, the more molecular motion, the more likely these collisions are going to take place. Now, this doesn't completely explain what's going on. For sometimes two components will come together, they'll smack into one another, but they won't have enough kinetic energy and they'll just drift apart rather than forming a new compound. So what is required is some minimum amount of energy, some sort of threshold energy. And so this minimum amount of energy required for a reaction to take place is what we call the activation energy. We might also call it an activation enthalpy. So what happens in these kinds of situations, we have these two molecules that smack together, and in that instant when they smack together, they form what we call the activated complex, which then precedes the product. So we can think of these in terms of a sort of what we call a reaction progress, what we call the reaction coordinate, which is basically just a measure of reaction progress. And then we have relative energy. And looking at a reaction, we have our starting materials going to our products. We'll just call these the reactants. Reactants going to our products. And in this case, we'll have the products a little bit higher in energy than the starting materials. And so the difference between here would be the delta H of the reaction. Products minus reactants, etc., leftovers from thermodynamics from last year. But to turn the products into the reactants, again, we have to go through this activated complex. And generally, the activated complex is higher in energy than either the starting materials or the products. And the difference in the energy between the reactants and the activated complex is what we call the activation energy. Now, the activation energy is basically, again, this minimum threshold that is required for the reaction to proceed. And if you remember our graph of kinetic molecular theory, dealing with kinetic molecular theories, if we have a number of molecules and the average energy of those molecules, if you remember that it would look something like this with this sort of curve. and this would represent the average energy. Sort of the root mean squared average kinetic energy. But what we see in dealing with the activated complex, only these molecules have enough energy to react to form the activated complex. So only these molecules right here are able to travel up this potential energy barrier. So they have to get over this, they have to have enough energy to get over this activated complex. Now, this is why reactions don't spontaneously happen. If you mix gasoline and you mix oxygen, they're perfectly stable. That's why we can carry around cans of gasoline. But you give enough of the molecules a suitable level of kinetic energy, and you will end up with a combustion. And so the trick is making sure that these components, how many molecules have the suitable amount of kinetic energy. As we raise the temperature, more and more of those molecules have that requisite amount of kinetic energy, allowing the reaction to proceed faster. More molecules, more collisions. So some smart person came up with the relationship. What they were able to do is they were able to realize that the rate for most chemical reactions is proportional to the rate constant itself. For any given rate of reaction, any given reaction, regardless of its form, rate is equal to Ka squared, as the only thing we really care about is these two numbers once we figured out the rate law. And what they spotted was that this was sensitive to temperature. So the concentration doesn't change with temperature. Only thing that changes would be the rate constant. And so they were able to determine that the rate constant was proportional or equal to some proportionality constant, which we'll call A, Euler's number, to the negative activation energy divided by RT. Again, we've seen this before. This is the universal gas constant. But here we're talking about in terms of joules. Again, when you deal with energies, we usually deal with joules, which is 8.314 joules per Kelvin. 8.34 joules per Kelvin mole. Now, we have to be cautious then that this means that our units for our activation energy would also be in joules. Though as you are well aware, we often see it reported in kilojoules, so we'll have to make those conversions. So, this is what we call the Arrhenius equation. So the Arrhenius equation in this form has this very ugly constant, which we call the pre-exponential. And how the molecules interact. It incorporates how the molecules interact. For us, we often ignore it. And the reason for that is we can express this in a linear form, where we take the natural log of K, that becomes equal to ln of A, the activation energy, divided by RT. And this is a linear form, and that means that we can plot natural log of K, or the natural log of the rate, and obtain a straight line with a slope of EA over R. If we plot this versus 1 over temperature. Again, the units for temperature would have to be in Kelvin. What this allows us to do is to graphically represent rate data as a function of temperature to get our activation energy, for the energy required to form this activated complex, which is actually quite useful in terms of how reactions behave. While this form is very useful to us, this is more when we have a table of data. This is very useful when we have a table of temperature versus rate data. A more convenient form is what we call the two-point form. We can get fairly, we can very quickly get to a different form of the Arrhenius equation that basically looks at only two different rates. Or rate constants, and uses that to tell us what the activation energy is. In that form, ln of K1, okay, so the first reaction, versus K2, second reaction, will equal the activation energy divided by R times 1 over T2 minus 1 over T1. And so this is what we call our two-point form. Allows us to measure the temperature, measure the rate at two different temperatures, T1 and T2, and calculate from those rates the activation energy for that particular system. It's very useful. Where this is very handy is it allows us, if we know the activation energy of a reaction and the rate constant at one temperature, we can use it to predict the rate constant at a second temperature. So it has a predictive aspect. This is very helpful industrially if we have a chemical reaction that we're trying to force to completion. We want it to speed up. Just like our other examples where we were looking at time, this is another useful technique where rather than predicting just how long a reaction takes, we can look at predict how long a reaction would take at a much higher temperature.